Here is the cord I was telling you about that I got at, I got one of them at Ace Hardware, and I ordered a couple more over the internet. It has that 5/16 spacing, which fits precisely on there. And I've got it plugged into a variable transformer over here. So what we're going to do is I'm going to bring the voltage up a little bit at a time, checking the amperage, make sure that we don't have any serious problems. And now we're up to about 120 volts. And see very little current. And we're actually getting a signal out of this. Now, I don't want to fool you, I actually had done this before I started the video, because I like to have two hands, one to control the variac, one to have my hand on the on-off switch in case I start seeing some smoke. So at any rate, the radio basically works, and that usually is the case if you replace all of those organic components that I talked about, like the electrolytics and any paper capacitors. Now this particular radio doesn't have any paper capacitors, so I didn't replace any of the ceramics. It does have right in here a little early version of a printed circuit board, and I'll show you that on the schematic a little later. Those sometimes do go bad. Generally what happens is the same thing that happens to all resistors that are made from carbon. The resistors drift up in value, and sometimes the capacitors tend to change in value as well. I didn't replace that because I tested as best I could from the outside, and like I say, I will talk about that on the schematic. But at any rate, I don't think it needs replacement. Radio seems to play okay without it, so the next thing to do is to measure this voltage off this selenium and see what we're getting there, so we can replace that with a silicon diode. So I've hooked up my meter across that 82 microfarad capacitor, which is the input from the selenium rectifier. Show you on the schematic what we're talking about. We're talking about this capacitor, so it's across this capacitor. There's the selenium rectifier. And what we're getting is about 104 volts. So we're going to write that down on the schematic so that we can duplicate that when we replace the selenium rectifier. And you may wonder, why do you replace it if it seems to be working fine? These are, once again, some of those organic components that the selenium itself isn't what fails. It's the oxide coating inside that breaks down with time, and as a result the thing will smoke. If you've ever had a selenium smoke, it is the worst rotten egg smell you've ever had. So if you don't want to have to put up with that, and I never want to smell another one, I always replace that selenium rectifier. So that's the next job. What I've done is I've put a diode in. There's the 4007 that I'm going to use. And I have my meter connected to the output of the selenium rectifier. It's reading about 111, 112 volts. That's this point right here. There's the selenium. And there's the 82 microfarad capacitor. So that's right there. Now what I'm going to do is I'm going to move that red lead over to the diode, but I'm going to turn off the power first since there's AC on the other side of that diode. Just want to be safe. And then I'm also going to put an 82 microfarad into the circuit to substitute for the one that's in there now. In other words, what I'm doing is I'm kind of prototyping this 4007 diode. You may notice how tiny it is compared to that big old selenium there. And that's the value of modern silicon electronics. They can build so much better equipment today than they could back in the day. However, as we point out, the silicon diodes are so efficient that instead of dropping 15 or 20 volts across them like the old seleniums used to, they usually drop about a volt. So we're going to have to get rid of that extra voltage somehow, and that's why we're doing this little experiment. Now I've connected the meter to the diode, and then I have an 82 microfarad capacitor across to simulate the circuit. And you see I'm getting about 137, 138 volts, something like that. For purposes of computing, what I'm going to do is I'm going to assume that there's about 135 volts with the silicon and 115 volts with the selenium. So I've got to drop about 20 volts. And so the next thing is to figure out what size resistor to put in there to do that. I think I'm going to start with about a 100 ohm resistor. But first I'm going to go ahead and put the diode in and put a resistor in series with it, take the selenium out. I've disconnected the selenium rectifier, substituted the silicon, it's a 1N4007, and then I've put in series a 100 ohm 10 watt resistor. Now I don't need 10 watts, it's just I wanted one that was plenty big. So and now I'm measuring the voltage off of there, and you see we're getting about 108 volts. So 100 ohms is just a little bit too big. Maybe about 80 ohms would be about the right amount. Now I didn't just guess on this. Depending on in sets that draw a lot of current, like a TV set, it's common to use maybe 20 or 30 ohms there. In a radio, somewhere around 75 ohms normally works in series. It depends on how much current that the set draws. So I'm going to see if I can find a 75 ohm resistor, and I'm going to measure the voltage across that too and see what how much it's dropping, so I can determine the current, and that'll help me determine what wattage. So I'll be back when I've done all those computations and ready to put the final circuit in. The next thing we're going to work on is testing the resistors. And resistors, particularly the ones from this era, are a little bit unusual in that they were made with carbon. By unusual I mean they don't really fit in that grows on the mountain category, but they still tend to change with age. In general, they tend to go up in value. So if you have a 10K resistor on the schematic, after 30 or 40 years, don't be surprised if it's a 20K resistor when you measure it. And generally back in the day, 20% was a perfectly legitimate tolerance. In other words, if it was a 10K, well, it might be as much as a 12K and still be within tolerance. I thought I might also show you, I mounted the resistor that was in series with that silicon diode. You remember the selenium used to be right in here, and I took it out and replaced it with a silicon diode. And I thought I would mention, I used two 2-watt resistors in parallel instead of a single resistor, because that increases the wattage rating. If you put two resistors in parallel, like in this case they're 100 ohm resistors, the resistance goes down to basically the parallel resistance value, which in this case, since they're both equal to 100, it's 50 ohms. But the power rating goes up. So if you have a 2-watt resistor and a 2-watt resistor, that basically is a 4-watt. And one of the reasons that they're mounted up in the air like that instead of down flat on the board, which might have looked a little neater, is because of what you see right there around this socket. And that is, these printed circuit boards are not real good at resisting heat. So truthfully, the further away you get components from that printed circuit board, the better. And then I thought I might also mention before I start doing this, I'm going to be using this modern multimeter. For some, in general, I would suggest this be the kind of meter that you buy. I don't mean this particular brand necessarily, but a good digital multimeter. The reason is they have high input impedance. They read out digitally, so you're less likely to make a mistake. And that's what I use for most of my measurements. I also, though, have some analog meters. This is an example. Now, this is a fairly good analog meter. It's made by Radio Shack. I'm not sure if they still sell it or not. The reason it's pretty good is it's got a lot of ranges, and it's 20,000 ohms per volt. Now, basically, all that means is the input impedance is pretty high. And for many radios, that's exactly what you want. You may notice here that it says the voltages measured to chassis with a VTVM. That's a vacuum tube voltmeter. Right back there is a vacuum tube voltmeter. They really don't make those anymore, but you can get one if you want. They have about 11 megohm input impedance. But the nice thing about these digital meters is they are a digital equivalent of that VTVM. And the reason I mention that is they have high input impedance, so pretty much anywhere that the schematic says use a VTVM, you can use that digital meter. Finally, be aware that some of the really old sets, this is, by the way, that radio is from 1962. This radio is from the 30s. And you may notice they've got a nice voltage chart there. But if you go down here, it says voltage is measured with a 1,000 ohm per volt DC meter. Now, back in the day, that was considered a pretty good meter, but today, you basically can't find those unless you buy an old one, because 1,000 ohm per volt really loads the circuit down. But if you want to get the same readings that these folks got at Zenith when they measured these voltages, you do have to use 1,000 ohms per volt. If you don't, one thing you can do is you can shunt the meter leads with a resistor. And the way you determine the size of the resistor, that is across here, to make it 1,000 ohms per volt is you look at the voltage scale, and in other words, what is the full scale reading that you would be getting. So for example, on this, if you were trying to read 195 volts, chances are the meter that you would read that on is a 250 volt scale. So 1,000 ohms per volt times 250 volts would be a 250,000 ohm resistor. And if you put that across those leads, you would get very close to the same readings that they got here. Finally, I'm going to quit here in just a second and go on to measuring the resistors. But the reason that I am talking a little more than normal in these, and I realize for some of you it may be boring, you know all of this stuff, and probably far beyond me in knowing about how to work on radios and so on. But I'm really aiming this video at people that are trying to figure out, for example, how to get into this and the kind of investment they're going to have to make. And so I'm trying to keep it as simple as possible, but I'm also trying to remember that when you start out in this business, there's a lot of little things that you need to learn that nobody really tells you about, and it's kind of later when they say, oh, you didn't know that? Well, you know, I went through that too. I started out in this business back in the 60s working on radios with a mentor. He was very, very nice to me and so on, but there were still times when he would look at me with a kind of strange look on his face and say, "You didn't know that?" So anyway, I'm trying to eliminate as many "you didn't know that's" from these videos as I can. So the last thing that I'll say before I start measuring the resistors is, in a tube circuit, you can usually do a pretty good job of testing the resistors by just putting the meter across them without unsoldering one end. But don't try that in transistor circuits, and even in tube circuits you might want to look at the schematic, because as you know, if there's something in parallel, say with that resistor, it's not going to measure what you think it is. So in general though, that means the resistor will read low. The nice thing about these old radios is the resistors tend to go up in value. So if you measure it and it's high, say more than 20% high, you can be sure the resistor's bad, because even if it's got something in parallel with it, all that would mean is the resistor is even worse than you thought, because even with something in parallel, it's still way too high. So anyway, I'll break off here and get on with measuring the resistors.